visiting chairs in Munich. These years, he had worked on developing variation technique for the passes, discrete-to-continuum, and on extension of gamma conversion to make it more suitable for quantitative analysis, local minimization, and variation evolution. Also, he had written 4 monographs, some of which have become commonly cited both as introductory and advanced reference. Today, he will give talk about discrete-to-continuum variation method for lattice system. Please.
Thank you very much. Thank you for the kind introduction. Thank you for being here. We have a repetition in sessions today, and thanks to the organizers for the very distinguished invitation. So the subject of my talk is the study of interactions between nodes of a network system as the number of the nodes that are into play increases. This may have a lot of applications and come from different fields of mechanics, physics, and applied science that we will keep in mind. It's a pleasure to acknowledge in this venue a worldwide collaboration between many groups that have been going on in the last 15 years. Here are some of the names, I will not quote them. And I took the chance to sum up what has been done by a group mainly in Italy and Germany, and trying to somehow find the main features of our research and what are the perspectives. So it's a good point to try to make this analysis. So what we have in mind? We have in mind systems where we have a problem of design of lattice structure, or we study biological tissues which have some kind of periodicity, or we can have networks, or more commonly we can think of the pixel of a computer screen, or the atoms of a crystalline lattice. Okay, this type of problems we have in mind have a common geometric nature, which is they have a lattice-like structure. So we suppose that there is a reference lattice or something that resembles a lattice, which can be a geometric constraint or come from some reasonable physical assumption. And since my field is variational analysis, I think of these systems as driven by an energy. So the simplest energy, and indeed we will mainly look at this type of energy, is what are called pair interactions. So the nodes of the nodes, there is a parameter which lives on the lattice, on the nodes of a lattice, which we call L, and between pair of indices of the lattice, we have some interaction which depends on this parameter, and then we sum up all the interactions. Okay. So the issue is to describe the behavior of a system when driven by this energy, when the number of nodes increases, and describing it with a continuum theory which is characterized by continuum energy. So replace the discrete to an approximating continuum energy. This is done what is called a discrete-to-continuum analysis, scaling the lattice. So instead of having a fixed lattice, we introduce a small parameter epsilon, and we scale the lattice. So here it's not written, but we introduce the lattice epsilon times n. Then we scale the energy, and this is a very subtle question. So what are the relevant energy that we scaling and transformation that we have compute this psi epsilon. We define a continuous parameter. This is done by defining a discrete-to-continuum convergence. For example, we scale the functions on the lattice. We have the functions defined on the epsilon and lattice. We interpolate them in some way, so we can compute them, for example, the L1 limit, L1 limit of these energies. And the requirement on this then to have a continuous approximation, an effective continuous energy, is that solutions to problems related to this scaled energy are close to the solutions with the same with relative problem related to epsilon to the continuum energy. Okay, and the E epsilon must be built up so that there is a relation between the solutions of the original energy E and E epsilon. So you don't have to read this slide, which is complicated, just to say that the outcome, the limit energy, will depend on the scaling and on how we define this psi epsilon. So it's the same type of E can be scaled in different ways and give rise to different limit theories. And this depends on the scale of the energy and the energy level that we are interested in. So this is a real multi-scale problem in which, in general, you have a superposition of a lot of effects. So the points of the talk will be to first highlight the variational methods that have been developed in the last 30 years that were thought maybe for the continuum that can be adapted to cover this passage, discrete-to-continuum. But so it's not just an adaptation. The discrete variable brings some additional effects. So we will see that we have difference in the problems that we can face, which simpler models, simpler answers than in a continuum, or maybe more complicated problems and answers. And in the end, not only we have some additional features, but we have problems that in continuum are harder to state and to solve. And now in the discrete setting, we can state new types of problems. Okay, first let's look at the general variational methods that we have in mind. So I will deal with a very simplified situation in which we have a simplified set of parameters. This rules out very interesting applications that have been developed in the last years, but still the general method will be described at the situation. So the situation is that we have a finite number of parameters. Actually, in almost all the talk, we have two parameters. So we have what is called a spin variable. So we can think of having values +1, -1. So at every point of the lattice, we put a label +1, -1. Then we have pair interactions, and we have what is called a surface scale. So the interaction between two points scales like a surface between the 2 points. And to have a pictorial representation, here we will represent, here it's a square lattice. Of course, mainly we will deal with two-dimensional case for drawing pictures. And we have a square lattice, and at every point we color the node either black, which is -1, or white, which is +1. And we have interactions that we can highlight as arrows between the nodes, so that have the same or different color. Now, in this simplified situation, actually there are two energies, which are the ferromagnetic and antiferromagnetic energies. Up to changing a little the variables, we can reduce to this situation of having the interaction between points is either of this form with sigma ij positive or negative. Sigma ij positive wants the sign to be the same in the neighboring nodes. So here we have a nearest neighboring interaction, but also farther away with interactions. For long-range interactions, it's the same. So if you have ferromagnetic interaction, you have uniform ground states. If you have an antiferromagnetic interaction, you have a microstructure which can be ordered or disordered depending on the type of interactions. So we will look at the first part at only ferromagnetic interaction. It's the simplest type of interaction. Still, we will see that we have a lot of interesting features. So this highlights the picture that we have in mind. We will have zero energy, so the energy are scaled so that the minimum is zero. Zero energy between points of the same color, and we can have some energy which is highlighted having also different color because the sigma j can be different. And we also put a dependence on epsilon because we always need to have some flexibility in our result. I mean, it's talking from experience, you will know that it's convenient to have some epsilon there because we will encounter problems in which you have some dependence on epsilon also on the sigma ij. So then this is a picture locally of what we imagined and what if we think of minimizing energy, so dots, points here we like to have the same color, but maybe they are driven by some external conditions to have some interface. So the idea is that some interface will be created, and in the limit we will have a sharp interface. Now we take in the limit, so you remember we are interpolating this minus ones and these plus ones, piecewise constant. So okay, if we have a piecewise constant function, we take in values plus 1, minus 1, and we expect the limit in the limit to see an interface where we have some regularity. For example, locally we have a normal, and the resulting surface energy depends then on the orientation. Okay. So as minimum problems are concerned, so if we are interested, if the approximation of problems is the approximation of minimum values of minimizers, then the convergence that is almost the definition of what we need is gamma convergence. Gamma convergence not only gives the convergence of minimum values of minimizers, but it's also stable with respect to perturbation if they are continuously converging. So here is the definition. You don't have to read it, but there is some notion which exactly gives the type of description that we have. And what energy we expect? We expect to have surface energies. Surface energies, then the limit function, we take the values plus 1, minus 1. We have some interface. And here we will, in the simplest case, we will expect to have an energy density, surface tension, living on the interface. To put everything precise, we need some geometric measure theory, but everything has been done long ago. So let's slow down a second to have a test problem which we can imagine our convergence. So the test problem is what is called the Wulff problem. So at least in the homogeneous case, so if the limit is homogeneous, then you have convergence from the convergence of a minimum problem. You have the convergence also if you add some volume constraint. And in the limit, the discrete problems are approximated by what is called the Wulff problem. So the minimization of the perimeter with a fixed volume. And this is, for example, and minimizers are called Wulff shapes, which exist, somehow are uniquely defined up to translations. And for example, for next to nearest neighbor interactions, so when we have interaction between the first and the second neighbors, meaning the diagonal neighbors, we have an octagon. So the octagon gives some information, well, the relevant information of what happens to pass it to the. And okay, if you want to make some exercise, here for the square nearest neighbor interactions, you have of course a square. For the triangular, by duality in a sense, you have an hexagon. and you can have more shapes depending if you add some inhomogeneity on the interaction. Okay. So the basic question is, does there exist a limit surface energy? So is this heuristic picture what happens? So or conversely, what are the microscopic requirement in order that this happens? So this has been explained in different papers, recent ones here. So suppose that now we are in the ferromagnetic case. So we need to have some decay. So we need to have some decay, and this is the correct decay, because otherwise the energy will not be finite on interfaces. So this is a necessary condition. Then we have to have something that forces the limit to have an interface, and this is a coerciveness condition. So we have to have that interaction, for example, between nearest neighbors. And then we want the limit to be concentrated on the interface, so not have some long tail which influences the limit. And so the long-range tail of this interaction must tend to zero. So with this hypothesis, then we have the existence really of a surface tension up to subsequences, of course, and which is convex in the second variable and positively homogeneous. Okay, so the limit is defined as functions are concerned on the BV lock with values in plus, minus, -1, but you can think equivalently as this as an energy defined on sets, so on the boundary of a set. So equivalently is defined on boundary of a set of finite rings. Okay. Maybe I don't have time to describe the proof. Now, these are the conditions, in a sense, necessary, sufficient to have a limit energy, but the method is flexible, and it's interesting to see that we have a whole range of possible variation. One is if we, for example, if we have weak interaction between nearest neighbors. So we relax the coercivity assumption. So in this case, we can have more copies, more sublattices, which are coercive between them, so they have good interactions, but they are not, the whole energy is not coercive, so it's not forced to live in BV. So in this case, we can have various copies in the limit, and you have an additional various sets in the limit, so with various interfaces here, and an additional bulk term. So we can have bulk term competing with the surface term. Or if we relax the control on the tail, then we can have non-local limits, which can be characterized here explicitly, or we can deal with the case. So also the periodic lattice assumption can be relaxed, looking at aperiodic lattices or even random lattices, and here there is some delicate point in defining random lattices. And also the ferromagnetic assumption can be relaxed in some way, but we have to force the existence of uniform ground states, so where it's 1 and -1, that can be possible also with some negative interactions. But I have only 2 slides where I talk about more parameters, but it's very interesting, so I have to mention them. So one, if we have more than 2 parameters, then we can have, of course, more than one set or 2 sets. We can have a network of surfaces, of hypersurfaces, which are parameterized then by the ground states of the parameter. So the minimal value for which you have the parameter for which you have a minimal value. So in this case, the problem becomes extremely more complicated. So it's not only convexity, so there is a role of these parameters which resembles the reasonings that one does to deal with quasi-convexity, and the condition become very complicated and also more rewarding because you have a contribution of interfacial microstructure which is not negligible. Another feature, if you have more than two parameters, is that you can have, for example, two minimal phases, +1 and -1, two uniform ground states, but still you can have a third phase, which is not minimal in itself, but influences the interface. So the interfacial energies, here is a picture of pictorial representation. You can have another phase, a zero phase, which lowers the energy. This is a typical expression in surfactant energy. And so we will have another variable now, which is a measure concentrated on the interface, which gives the amount of the third phase. And there are some extension to positive temperature. So there is also extension to some evolutionary framework in the spirit of motion, of minimizing movement, which has been applied to sets to give a definition and the proof of motion by mean curvature by Algren, Taylor, Wong, and then developed by the Giorgi and Ambrosio Gili some time ago. So the idea is to have an implicit Euler scheme in which you minimize not only your energy, but some dissipation, which is usually interpreted as L2 distance of the interfaces, and introducing a time step parameter. So you introduce a time scale tau, you minimize recursively the scheme, you obtain an orbit, which you prove being every other continuous, and then if you scale it properly, and then you can define the limit up to some sequence. And then, so this is a kind of gradient flow along the sequence E epsilon. Okay. And this has a connection that you can see from with the static analysis, because I said gamma convergence is compatible with the addition of continuous perturbation. So if the dissipation is continuous, then you can pass to the limit in this problem. And if tau goes to zero slow enough, then you can deduce that the evolution of the limit energy is approximately the evolution of our discrete set. So with this you can deduce something. You can deduce the evolution of spin systems in terms of the evolution of the limit, which is what is called a crystalline perimeter. And crystalline perimeter has been studied by Algren and Taylor a long time ago. The motion related to minimizing movement related to crystalline perimeter is what is called flat flow, which is motion by crystalline curvature in which the sets move according to the crystalline curvature, which is, for example, defined for a rectangle as the inverse of the length, or twice the inverse of the length. So with this, you can conclude that this is crystalline motion by mean curvature is approximately the minimizing movement for nearest neighbors ferromagnetic interactions, but only for slow time. So what the second point is that you have additional discreteness effect. So one of the effect that we have seen is an easier, more flexible model. So we have seen that we obtain, easily. We have seen that we obtain, but you can believe it easily. Theories like multi-phase materials, surfactants, double porosity media, which in the continuum case require complex geometrical topological assumptions. They are in some cases very complicated to model. Thanks to the non-local character, say, of discrete interactions, then you can obtain this with very, very simple model, like the Bloom-Griffith for surfactant and so on. Then it's very useful also this discrete-to-continuum analysis to model low-dimensional objects. Low-dimensional objects like thin films, nanotubes, in which you can couple this process by a dimension reduction procedure. And for these objects, you have continuum theories which have some properties to which you can add some properties depending on some microscopic design parameters like the number of layers. For thin films, the thickness of a thin film, in a sense, doesn't matter. As long as it's thin, the theory remains the same. Here, the theory is different, depending on the number of layers, and it will be really, really very different. And another exciting, if you want, field is the modeling of quasi-crystals, which can be viewed like irrational thin films. Irrational means that the normal is not a rational direction. Okay? Irrational thin film in higher dimension. So, for example, Penrose tilings can be seen as a hyperplane through a two-dimensional hyperplane, say, in 5 dimensions. And so there are problems, as I hinted at, that are easier to state and to solve in the discrete setting. Some kind of optimal design problems, which is the optimal design problem is the construction of structures with extreme properties subject to design constraint. And usually the construction is carried on by the careful notion, the careful analysis of homogenization formula. That in this case must be non-periodic, non-linear, non-convex by the nature of our interactions. Okay? And in the discrete case, these optimal design bring more flexible results. I would like just to give you an example, which is very, very simple. For example, you can think of computing all the possible interfacial energies of mixtures of two ferromagnetic materials. So you want to understand what are the extremal properties that one can obtain with some design constraint, which is, sorry, I can't use this. In this case, is that the coefficients belong to a set of two parameters. So this is the design constraint. Okay, and this in the continuum we don't know how to solve this problem. So there is a continuous analog, and there are bounds, and the bounds rely on the use of layered materials. So the idea is that layered materials have extreme properties. Unfortunately, they have different extreme properties in the different directions. But we would like to have to optimize, to have some structure, we optimize the same property in this direction, and this is done in the discrete setting. So in this discrete setting, you can construct. Here is the picture. You don't have to follow the details. You can have discrete lamination, which are lamination optimized in the same properties in both directions in these two-dimensional case. Okay, so there's another slide here that you don't have to look at. It just says that you can describe explicitly all the possible surface tension that you can obtain in terms of the Wulff shape. Here is a possible Wulff shape, and here are lines that represent the bounds on the discrete, red, and on the continuum, blue. And they are different, and they are very different. Okay? And the bounds on the continuum are not proved to be optimal. So there is a difference of type of results that one can obtain in the discrete. And another flexibility of the discrete setting is the possibility of very easily introduce random dependence on the coefficient. So a random distribution of the coefficient, which is, for example, you can think of having a random distribution of defects on a ferromagnetic materials. Maybe some of the nodes, some of the bonds actually have a different structure, so coefficient. You can think, for example, going back to the optimal design problem. Now, instead of having a deterministic distribution, having a probabilistic distribution of alpha and beta with probability p of 1 minus p, following some random ID random variable, for example. And so the problem that you can ask yourself, and that we solved together with Gatnitsky, prove that you have a limit, and the limit, so the whole sequence converges, so you have homogenization, that the limit is deterministic, it doesn't depend on the realization of the random variable, and you can describe it in terms of percolation formulas. So there is a link between the variational theory and the theory of percolation. So these are two different communities. We think of energies, they think of universality, of criticality, and so on, but there is a way to connect the two things. The two things are not, the connection is not painless, so you have to work hard to make a connection, but I think it's very rewarding. And as a result, you can also have the proof that there are percolation thresholds, for example, for dilute spins or rigid spins, where you have some limit degenerate case of the coefficients alpha and beta that you consider. Okay. So this is another slide saying that you have an interplay between percolation techniques, percolation results. So understanding the properties of percolation clusters, then give proofs that provides the possibility of proof, representation theorems, or homogenization formula, and the interplay between those two things is in both ways. So you have interesting variational percolation questions. So these are not the questions that percolation people usually address, and they seem to be interesting in terms of percolation theory. And conversely, you have new variational problems that come. I have to say also there are a lot of effects in the evolutionary case. So in the main the starting point of the observation that we have to make is that for a discrete system like this, if you have a fast time, so if you think if tau is going to 0 fast enough, then you can think that you're evolving a discrete set. But evolving a discrete set here means that it will be stuck immediately, because all points are local minima. You have a discrete set of a discrete set of variables. So if tau is very slow with respect, is very fast with respect to epsilon, goes to 0 very fast, the motion is p. This implies that since we know that conversely, if you have slow time, so if epsilon goes to 0 fast enough with respect to tau, then we have the limit corresponding to we have the evolution corresponding to the gamma limit. So there must be something interesting inside. There will be some critical dependence on tau and epsilon, for which you have a non-trivial evolution. So an evolution which is not the evolution of the gamma limit and is not been. A simple example, but not so simple, it took some time to prove, is a paper with Gelli and Navaga, in which we flow the nearest neighbor ferromagnetic interaction on the square lattice, and there we compute the limit. So the limit is not the motion by crystalline curvature, but it's a kind of discretization of the motion by crystalline curvature. So the critical scale is when epsilon is of order tau, so you can suppose that epsilon over tau goes to some gamma, and now you have the velocity is not proportional to the curvature, crystalline curvature, but to 1 over gamma, the integer part. So it's a quantized velocity, if you want, and in particular, this says that the velocity is 0 if the curvature is small enough. So it's 0 if you have large sets, large depending on gamma. And as gamma goes to 0, everything is pinned, and as gamma goes to plus infinity, of course, this turns out to be simply the curvature. So you have an effective motion that describes as limit cases both the pinning and the motion by crystalline curvature. So one could think that it's a kind of, the effect is just a kind of discretization coming from the discrete variable. It's not. Actually, there is another recent paper by myself and Schilla in 2013, where we analyze a similar case where the gamma limit is the same. We have introduced some defects which do not influence the gamma limit, but they influence the velocity. And the velocity is influenced in a very non-trivial way. You have to solve a dynamical system to prove that it converges to a asymptotically periodic orbit, which characterizes the velocity, the mean velocity of this asymptotically periodic orbit, characterizes the homogenization formula for the velocity. And so these are, I think I have conveyed the idea that you have a lot of problems. So a lot of effect of discreteness that are a surprise even to me. So every time I think that I have concluded my study so I can move on, let's just look at this other case. You find another interesting effect of this partial discrete-to-continuum. The last part is something more in progress. It relies on the effect of patterns and microgeometries, which are automatically or more or less automatically obtained if you have antiferromagnetic interactions. So if you have antiferromagnetic interactions, so the coefficients are negative, then the value, the spin want to be non-aligned. They take the different values, and you can have ground states, but ground states may be what's called frustrating. Frustrating meaning that on a ground state, you can have some pair interaction which are not at the minimum. So not all the interactions are minimized for ground states. While for ferromagnetic interaction, of course, they are all minimized. And this brings lattice microstructure. Here are simple examples. In the triangular lattice, for nearest neighbors interactions, then of course you can't have all the bonds happy, because you have 3 bonds, and 2 must be of one kind, the one of the other, or all 3 of one kind. But so here I have highlighted in red the bonds that are not happy, the bonds that are not in the minimum. Okay, so here it's a configuration that locally is at the minimum, so you can't go below this energy here. So you can have disordered ground states, but you can also have ordered ground states. This is the case of the next nearest neighbor interactions. So you have the nearest neighbors and second neighbor interactions here, antiferromagnetic, and you can have 2 types of minimizer. This is more interesting, depending on the values of the sigma ij. So depending on the sigma ij, you can have either this usual checkerboard or stripes. Well, even if you have antiferromagnetic interaction, you can have, for example, for nearest neighbor interactions on the square lattice, you can have non-frustrated minimizers, ground states, like in this case, which are maybe less interesting. So, first observation is that the parameter we are starting with is meaningless. So the parameter +1 - 1 doesn't make sense in the limit. Why? Because you can have, for example, ground states like in this antiferromagnetic nearest neighbor interaction, which have equal number of +1 - 1. So the average here is, so you can expect of having some limit, the weak limit, but the limit will be 0. Will be 0 on this side and on the other side. But you have an interface here. If you look here, you have an interface where you can see a difference between the two sides. Here you have two sides which are not exactly the same by a period, and here the period is 2. So you can't superpose this side to that side with translation equal to 2. Or conversely, you can have an interface, but it can carry no energy, like in the triangular lattice. Here there is an interface. You have on one side some frustrated minimizer, on the other side some frustrated minimizer, which are a certain shape, but there is no energy here. The whole thing is another ground state. In this case, we talk of total frustration, so where you have no interfacial energy between ground states. Okay, but still you can have a description. A description in which the limit parameter is the ground state itself. So let's go back to previous slides. Here we have two ground states, and we have seen there is an interface. We can these two ground states are different, so they can't be superposed. So you can formalize this. Suppose that you have a finite number of ground states. These are periodic functions, which are minimizers. I don't give the precise definition because it's complicated. And between two of them, there is a positive energy barrier. So you can't go from one to the other, staying at the minimum. And then you have to assume, of course, some surface type decay. Otherwise, we are seeing you can't obtain a surface energy. Then there is a representation. So the first part it's hard to read here. It says that locally, if you have a sequence with bounded energy, and locally the sequence must look like one of these ground states. And what is outside, it concentrates on the surface. And then if this is the case, then essentially you can take the ground states as parameters. So you have something which is parameterized by these n numbers or these n ground states. So for example, you can have for the next to nearest neighbor interactions, you can have 4 types of striped patterns and interfaces between them. If you add a ferromagnetic interaction to the triangular antiferromagnetic lattice, then you stabilize and you obtain 6 parameters. Then you have something described as by 6 ground states. Here you have another case in which you have 16 ground states, and of course, as you increase the number of interactions, you can have more ground states. And now everything becomes more different, more difficult in this framework. For example, even the simple homogenization problem, where you want to homogenize, you want to describe the limit when you mix ferromagnetic and antiferromagnetic with equal proportion. For example, you can obtain something which is non-frustrated and has a surface energy of crystalline time, or which is frustrated and has an energy only in one direction, so it's a degenerate energy, or a surface energy, or totally frustrated. Okay. Okay. I have to say that there are a lot of interesting problems. This involves also, especially in the probabilistic setting here, where we want to choose randomly +1, -1, and this microstructure also has an effect, for example, on thin films. So thin films become very interesting when you have antiferromagnetic interactions, even though because the number of ground states may depend on the layers. Not only that the outcome, the energy density depends on the number of layers, but also the number of ground states. And you can have, this is a case in which you go from 2 ground states to 6 ground states, which is the bulk number of ground states. And this is another case in which you have the antiferromagnetic triangular lattice, which is completely, totally frustrated in the limit. And now the number, these are not frustrated, these are not totally frustrated. You have interfaces, but the number of ground states increases exponentially. I have to say, finally, that also you have interesting things in the evolutionary setting, where you have motion by the creation of microstructure, which can be point creation, point microstructure, point defects that move, or bulk defects that are annihilated along the surface. And you can also have a way to define some backward motion by crystalline curvature, looking at minimizing movement for antiferromagnetic materials, which are not possible in the continuum setting. Okay. And with this, I conclude, and I hope we have touched not just the tip of the iceberg, because we have seen only the surface case, only when you have 2 parameters, essentially, and there are a lot of very interesting results in other scales, and I think there are very many problems that are yet to come. Thank you very much.
Any question or comments? Okay, since we don't have much time, okay, thank you very much again. The next